Alright, welcome back to our stack language development. So for today I was thinking let's just start re-implementing the language in itself. And I have some changes which I did, and I guess it's kind of important, but I'll just put them as an update, and if you want to check that out it's fine, but I'd say that the language looks basically the same. I just added like constants just to make stuff easier, and also remove some things from the data structures, because I thought it's going to be easier to just use pointers, and then data structures are just wrappers around the basic types. So that's going to be much easier. So all the tests are fine, we don't have any changes, that's perfect. And the idea would be to now no longer change main.c unless it's really needed. It's already 4,000 lines of code, so that's kind of interesting. And I would say we could start on the stack.sl file. Right, so this is going to replace main.c. That's my idea. So how is this thing gonna work? Well, first let's start with our basic main function. Right, so main stack.sl, and basically we have our lexer, which is going to tokenize the file. I think I'm going to skip this part for the start and just pick up the things from the parser stage, probably, just to get some assembly going, like have the stack compiler, like the development loop happen really fast, so we can do the lexer at some other stage, because but have the code in the file itself somehow, so like an interpreter, if you will. But so we have the parser, and this is kind of the starting point that I want to use for today, and then while I'll just do the lexer. Okay, and we have like more stuff. So we also have import stdlib, which I think is gonna be kind of painful to add at the beginning, so we'll see how we can do that as well. But hello world basically looks like this in the language. So string.stdout, and now it includes everything, and we can do like type checking. Okay, I forgot about the return. That's fine, that's why we have type checking. And then generate the assembly, put it into example.asm, and then if I try to use the FASM command, so it's something like stack.sl and we run it, right? We don't have yet running FASM or LD from the compiler code, but we'll have that in the future, so it's gonna make everything much easier, I think. So yeah, let's think about how do we want to start. Right, so we are going to import stdlib, right? And I guess instead of just creating a file, so I could just make like example dot, we already have example dot sl, right? We could have something like this, and just try to tokenize it and everything, but I think it's gonna be more fun if we just try to generate some assembly instantly, like right now. So yeah, because I tried the other way around when we did cool language, and I didn't really like it to start with the lexer. It was kind of boring, but let's see how we can do. So probably I'm gonna use main.c as inspiration somehow. And let's imagine that we have already a lexer and the parser, and we just generated the AST, so the prog. Right, so let's imagine we generated the prog. Oh, I don't have haven't started. It's strange. Main.c. So let's see. Let's take a look at prog, right? The data structure. So it's kind of important, I think, to define things in order, but I think having only one array would be nicer, because that's how I did it for the type checking, having only one array of symbols. But at the same time, it kind of makes sense because our language doesn't have unions, so it's gonna be harder to do that. Okay, anyway, let's go to stack SL. So the idea, right, would be to, let's see, we have stack data, we have stack AST node, which is like the basic part of our data structure. Right, we have stack AST node and data. So I would say we can start with a function. The function, like function main, for example. But for that, yeah, I think that having data stack AST node sounds good. So it would be like a string for the name, right? That's how I do it, but I think it should be value, yeah. It should be the value of that. It also has the position, but let's not go that far yet. So we have stack AST node, then we have stack AST function, and basically a function should have arguments, returns, and the body, and also the name. So I can have stack AST node name, and yeah, could also make sense to, let's just say, have the name. Because we don't have arrays, right? Like we could use a PTR for the array, that makes sense. We don't have a data structure for the array. Maybe I should have added that first, just to make things a bit more smooth, but let's just ignore that part. So then I guess stack AST function is kind of used in the stack AST prog. Stack AST prog, right? And that's what I meant. We kind of need arrays to make things easier. So functions, right, they need some arrays for these parts, and then data needs arrays for the fields. That's kind of that. So next part, I guess, if we want to go in that direction, we should add the stack assembler. Right, stack assembler, and guess for the beginning, so stack assembler init just does some initialization, not interesting. Maybe just going straight to stack assembler emit. So something like data stack assembler will have something. I'm not sure yet what fields it's gonna store, but it's that. And then we should have something like stack assembler dot emit, and I would say stack assembler is the first argument. Then the second argument should be the program. So stack ast prog. Right, so we have the assembler and the ast on our stack. I forgot about the in. Right. And what do we want to return? Not sure. I don't think we should return anything. Like if it fails, it fails, and we crash. Okay. So I mean I already have an idea maybe what I want to add in this. Maybe it's gonna be the file descriptor where we want to write. Right. So maybe int fd for you know where do we want to write this assembly. That could be something. And yeah, I have this function emit, which I kind of use it to just print stuff. So yeah, and this is the first thing that we need to emit. So maybe I could say that emit, so function emit should take in stack assembler and some string to show, and it shouldn't return anything. So assembly and the string. Right. So probably we need to swap the first step is to swap. That's pretty nice. Then we dupe our assembler, we put the string that we want to emit, right? And then we call to emit function. So at this stage we still have the same ast and assembly on the stack, or at least that's what I hope. Right, so this should print format elf64, which is the first step. Nice. Okay, so we want a file descriptor. I guess I'm just gonna say that the file descriptor is gonna be std out, and we need stack assembler.init, which, as I said, doesn't exist anymore, so we have to implement it ourselves. But I wouldn't say, I don't think it's that difficult to do. So stack assembler, and I guess my approach for this stuff, if we check out stdlib, oh, I don't have that anymore. I had something that you could use as an example, but let's just do it manually. So I would do something like const value, and then let's call it stack assembler dot size of, and this is the size of our assembler. And yeah, like constants aren't really constants because they're just gonna be functions that don't take any inputs and just return something, right? So if the function is like that, like doesn't take any inputs, it means that it can be somehow computed. I mean, it's not really true because you can use read and stuff like that, but I mean, I guess the idea is kind of like these are functions that only return stuff. So yeah, I don't know, because I think that doing the same thing but calling it size of and then int in 8, it's a bit more annoying, and this is shorter. So yeah, I don't know why. I thought it's gonna be more fun if I add it, so why not? And maybe in the future we can actually make them constants. So yeah, and then we have fd offset is 0. So now we can implement, Well, actually, we first need to implement the init function, which is more important because we want to create something. So we do stack assembler.size of, and then we pointer.alloc. All right. So this is going to give us, well, we have an fd already. We have the fd, we haven't changed that, and we also have a pointer. Right, that's what we have on the stack currently. So the idea would be to because I kind of have an algorithm of how to do this part, right? So the idea would be to duplicate, because we want to keep the pointer, right? We want to have fd ptr ptr because we want to keep the pointer until the end of the execution, right? And why do we want that? Well, we have a special function, pointer.stackassembler, which is automatically generated, that takes a pointer and it just casts it to the data structure. So basically right now pointers and data structures mean the same thing, but because we have static type checking, we cannot really cast between them, you know, via inference. We have to do that manually. So again, that would be nice to do automatically somehow, but maybe it's not a good idea because then the language is not really that static, if you know what I mean. So yeah, it also makes sense to explicitly say that now we converted the pointer to a stack assembler. So it's like calling the constructor in a weird way. So then I would call rotate. Right, so I just bring forward the fd. I guess I could just do rot prime. You'll see why in a second, and that's because fd is going to be second item, right? Then we do stack assembler fd offset, and that would put on the stack fd ptr and 0 for the offset. So now the idea is, how can we add these two together, right? Well, we have a special function for that too, and that's just converting the pointer to an integer. So fd ptr int, sorry, yeah, because the integer is basically the same thing as the pointer in this language. So pointers and integers, they look the same on the stack, right? They're just numbers on the stack. So if you should be able to change between them when you want to. And yeah, the reason why we need this is to add offset to our pointer, right? So we add this offset to the pointer and then we convert it back to a pointer, right? So now on the stack we have fd pointer plus, I mean it's plus 0, but it's still nice to keep the same algorithm, right? Because maybe we can just convert this into something done automatically. But yeah, the idea is right now we have this conversion between types, right? And pointers and integers are usually the same thing. Even in C you can convert from a pointer to a long and from a long to a pointer, right? And just use them interchangeably. So I guess just to understand better, you have to think of pointers more as numbers rather than addresses. So like they are nothing special, right? They are just numbers, and you can see that here, that we just interpret them as numbers so we can change them. And you know, again, we don't have plus on the only data type we have plus for is the int data type, so that's the main reason. Anyway, let's continue. So what do we have to do next is to swap these two, right? We swap. So now we have the pointer plus 0 and fd, And now we have that special function from stdlib that is supposed to write the pointers, right? So, and again, the only things that we can write to a pointer are integers and bytes, which are, I mean, they're also integers, but we just imagine that we only use the small part of the integer. So yeah, it's like writing only 8 bits from the integer. So yeah, it's still an integer, but we only write the first 8 bits of it. So yeah, anyway, let's call that. So it's gonna be pointer store, I guess this one is store now, and we store an integer, and this function removes these two from the stack, right? So that's its input, pointer and integer. So the idea is that now at this address we wrote fd, right? So it's a difference between pointer.int and pointer.!int. This one just converts a pointer to a number, just like we just look at its value, or I guess, because usually when you say value associated with a pointer, you mean the thing that it points to, but in this case we just want to see what its number is, what the pointer itself is as a number. And here we want to go to that value that it points to, right? I mean it just happens to point to a value, so we just go there and write fd there. So yeah, and this would be like a small algorithm of writing fields in a data structure. You just have to replace this fd with whatever field you want, and that's it. And yeah, it's gonna be interesting for nested data types if we keep the same logic here, but I'm pretty sure yes. Probably you have to just change the data structure to a pointer. So for example, for integer it would work to say int ptr, then ptr.int, but imagine here you have, I don't know, string, right? Or something, right? So, but I guess that's not really needed for integers, but we can keep it there just to showcase that, for other data types. Depending on the data type of the fd, you just change the name of the field and this type, and it should, I think it should save any field. So yeah, something like that, probably it works. And at the end we just have a pointer which we convert to our data type. So I think that's pretty good. Right, so let me just remove that. Right, and cool thing is that this is the entire algorithm. So you start with fd and ptr, you duplicate the ptr just to save it, and then you push it back, and then you just store the first field, and then if you call this again you store the second field, and so on, right? So that's the idea. And again, this might make it easier to just implement initialize somehow automatically, right? So yeah, and even these functions somehow automatically. But yeah, we have the stack assembler, and as I said, we initialize it with stdout. So this is the assembler. Let's leave a 0 at the end. Right, so the first step is to just call emit, but we need a program too. We need stackast program, which doesn't really do anything. So yeah, that's gonna be interesting. How can we implement that? stack ast program. And if I say 0 and then just have an init function, that's basically not gonna do anything. Right, so we can just allocate its size, and then we can just stack, or I guess ptr.stack ast prog. So yeah, I think this should work. I'll see if the compiler works probably with 0 fields. We'll see that together. So after that we need stack ast prog. So we have the assembler and the ast. We emit, we don't have anything left, and that's that. Expect the name got comma, line 31. Oh, I called it data, it should be function. Not sure why I said data, but function emit. Oh, so yeah, we have to implement emit now. So as I said, we want to write to the FD. So can we do in stdlib? So in stdlib we have this fwrite, which takes in file descriptor and a string. So we should do something like swap stack assembler.fd, swap back, and now we have file descriptor and string. I would also like to put new lines after each thingy, and we still have fd and s, right? And we can just say stdlib.fwrite, and this thing should just write to the okay. And stack assembler emit has non-matching expected but got stack program and stack assembler. Okay, so we have to just pop 2 at the end because we no longer care about them. Stack assembler fd is not defined, so we have to define the fd function now, which we can also see how we do that. It takes in a stack assembler and returns an integer. Right, so I would say first step is to just convert the stack assembler to a pointer, and luckily enough we just have a function ready to do that. Then the next step, if we just do it not thinking that much about it, we should add the offset to the ptr, right? But again, to do that we have to convert the pointer to a number and then convert it back. So now we have ptr plus 0. Again, it's kind of pointless, but it's nice to have it. So we have the pointer plus 0, and the next step is to just read an integer from that position. Right, so ptr read int. Now I was just thinking, right, like for more complicated data structures, who knows, maybe it's gonna be more complex, but for integers we just read the integer. So let's see again, stdlib.fwrite. So we stdlib. Line 34, excuse me. So I guess fwrite if we check this out, it returns a boolean if it was okay or not. So we can do something like not if, then we panic, and then phi. So this is just like doing an unwrap. Maybe we should call this one unwrap, but yeah, whatever. Yeah. Okay, so we just get format elf64 and the new line. So that's kind of cool. That's a good first step, I would say. That's right. That's a pretty good step. So, right. Obviously, we could add all the assembly here. Not sure if I want to do that though. Like we can emit the allocator. And emit the keywords. You know, for the keywords we need all of these. So I guess the first step that's true should be writing the allocator, because that's gonna be needed in our main function. So I'm gonna take all of this stuff, right? I'm gonna take all of this stuff, and maybe we want the function stack assembler dot emit dot allocator, and maybe it just takes the same arguments, stack st prog, although it's not needed, but you know, so it takes in the assembler. We have all of these emits and then end. So as you can see here, we want to have a dup, then we want the string, and then we want emit. So let's try to get to that point, right? So it's gonna be kind of annoying. Maybe I can just do, let's do a macro. So I guess we just go to beginning, delete the emit, write dup space in the parentheses, go to the end, maybe delete the, that didn't even matter. We go here, we replace this with emit, and that should be it. If we also go down, and that's it. Okay, so I think this should work. I'm just curious if it's gonna work. Holy, what? Oh my. Okay, let's go back. Okay, I forgot about the semicolons in the thing. Okay, let's start from the beginning. Okay, it's not meant to work first try. That's always how it is. So we dup, we delete the stuff, we delete that, and then we emit. Okay, so now it looks better. Okay. So yeah, it's really it sucks, right? So much stuff. I guess somehow aligning everything would be nice, but yeah, I'm not even sure. Maybe we want to just remove comments from the final thing, because why do we have comments, right? They're kind of pointless. I mean, they're good if for debugging, but yeah. Right, but I don't want to waste your time, I guess, on doing that. And now there are these these things with stack word size, for example, which I'm just gonna hard code. All right, let's just hard code them, and that's kind of everything. So I'm just gonna remove comments and stuff like that, make the code a bit prettier, maybe, if that's possible, but yeah, whatever. So then we have stack assembler dot emit dot allocator. The problem is this needs a swap, dup, and then swap at the end, right? Just to get the same format. So now if we run this thing, I guess at the end here we need to pop. Wait, how did you get? Okay. So we don't have to swap. That's nice. So you can see it prints all the assembly, just the same stuff that we had before. Okay, anyway. So what's the next step? Well, I would say emit the entry point. Keywords, I'm not gonna do them yet. Then program and then constants. So program would be our focus, but we also need keywords. So we'll see how we can achieve that. Anyway, let's go to entry point, and I'm just gonna copy just the entry point, right? So function stack assembler dot emit entry, and it needs a stack assembler. Okay, here it's just in, but and yeah, what's interesting is even this one needs this mapping. So we'll see again how we can get there. But for now, let's just emit everything. Here at the end, we just need to pop. Right, and this one I can just hard code for now, and let's say it's gonna be function 1, right? And that's kind of it here as well. So we just do the same entry. And I guess now is interesting with emit program. The emit program part. But again, the order doesn't really matter, so the order in which we emit the stuff. It's kind of nice. So you can see here we call to the function 1 or main. So that's what I wanted to just simulate doing that manually. So just creating the data structure with the main function, and let's say the main function returns 1 or something. So that's kind of it. Yeah, but we kind of need arrays for that, which, I mean, let's just do arrays. Why not? Let's just do a bit of funny. So it's gonna be array. I think I'm just gonna call it array. It needs integer capacity, integer count, and pointer items. That's how I just define it in ds.h, right? I think that's fine. You can even see a more complicated init now, I guess. I guess at least that's fine. Implementing array, so array.init is gonna be int, and I guess it's just int, or not even that, it's just the initial capacity. I mean, I could do just initial capacity, but let's just say that I implement it the same way I do in ds.h. So input is not going to be anything, right? So capacity is 0, the count is 0. How about pointer? I could set it to 0. Or some, so we are gonna allocate the size of the array because that's needed. So let's say constant array size of is gonna be 24 because we have 3 integers. I guess I could use stdlibs int size and say int size 3 multiplied, right? So we have 3 integers because pointer is just integer, and that's the size of, so we can just allocate it. Then here it's array capacity, and we need the offset of each thingy. Capacity offset, the first offset is 0, the second one, which is just count, is 8, and wow, items is 16. I could just say int size or multiply with 0, multiply with 1, multiply with 2. So we have array capacity offset, we add that, then we convert it to a pointer, we swap, then we do int ptr int, and we write. But what's interesting is this comes in the reversed order. Okay, so here, as I said, I want to do 0, 0, 0 for everything. Alright, so this is the capacity, this is the count, and these are the items. I'm just gonna say capacity, count is len, and the items are axis. So cl axis, right? So if I do rotate prime, how is the stack gonna look like? Well, it's gonna be c l ptr axis axis ptr again, sorry. So first thing, we store the axis. So again, we just store it as a pointer, which is not really gonna care, so it's gonna be fine. All right, so then the next thing we store is gonna be the count. Again, we just take them in the reverse order, and the capacity. So it's fine, we make everything 0, right? And here we can just say pointer array. Right, so I mean, we don't even need to say this stuff because we know already. Another cool function would be function array.append. And now comes, oh, another thing that maybe I forgot to store is the size of the item, right? But I think storing items is gonna work using pointers. Right, so you give an item and you store the pointer. So that means if we take a look at ds.h, ds dynamic array append, you can see that it takes in a pointer, so that's no problem to do. So I would say it's gonna be definitely the array. I kind of don't like giving it a pointer. Maybe it's also returning status code, or just boolean if it worked or not. So it could be like an A. The problem is I don't have a.ptr. Right, and a.ptr is not really that useful either, because what does that function do? It depends on the type. Because for example, integer, I mean, no, not really. Integer.ptr is just it, but yeah, like it should be ptr here. So what are we gonna do in this case? We have the array and some pointer, right? And we want to store this pointer in the array. Interesting. Maybe we want to give it an initial size, and I'll just implement a proper one later on. So let's say I'm gonna do, I don't know, like 1,000 items. Is that gonna work? Like 16 items. So if I want to allocate 16 items, I could do stdlib. Because I kind of need this memory needed, array memory needed. So it should be like what, 16. So it's gonna be obviously this thing, but I think I need 8 times plus. So imagine 16 times 8 plus this thing. Right. Maybe it's just 15 items, but let's do 16. So I could do something like 16 array.memory needed, and it's like, yeah, whatever, duplicate, but maybe const array temporary len, and it's gonna be 16. So we allocate 16 thingies. Right, so we try to append, right? And maybe the first thing we need to do is obviously swap pointer array. Let's say we do dup and then array dot count, then we dup and do array dot capacity, so we get pointer length capacity. If the length is greater or equal even, we just ptr. So I would pop and say it didn't work, but here it's like to do realloc pretty much. right? So that's the idea. And on the else case, it means that we got the count. Oh, here actually. Okay, so I do this call, so I get ptr array, or I guess al. So I have to swap dup capacity, so I get l ac. So it's gonna be easier to just say rot less than is the bad case, right? Because we bring L forward, so C is less than L is the false case, or equal, and here we have pointer and array, so we can do stuff like dup array count pointer al. So L is gonna be the place where we want to do stuff, where we want to store the pointer. So then I would maybe, let's do a dup2, so we get ptr al, we can swap, then do ptr int plus int ptr, so we base, and then maybe just that ptr al, and we have a plus l now, so that's not right. We should have done array.items actually. So now we get axis plus l, right? We converted this array into an axis, and we add the length, and then we convert it. Well, yeah, it's still ptr.int, but it's the extra step we needed. Array items. So we get axis plus l, and this is a pointer where we want to write a, which is also a pointer, funnily enough. So let's rotate, and we bring it forward. So l axis plus l a. I will just change the pointer to an int, so it's still the same thing, axis plus l a. But now what we can do is just int, or I guess pointer store int. So we just get a pointer. Oh my god, what the fuck am I doing? Yeah, it's annoying because I call this a, I guess, a pointer. It's pointer, the thing we want to store, actually, not a. Yeah. So it was fine up until this point. Then I need to use rot4, which in the end I had to add it because otherwise it's impossible to do anything. But l axis plus l ptr. So the pointer now became an int. So we store it. Al axis plus l disappears. We need to increment this thing with 1. So we have al plus 1. We can swap. So this thing should return a boolean. Let's keep that in mind. We swap, so we have l plus 1 a. L plus 1 and a. And let's just convert this thing again to array. No, we do array.pointer because we want to set the the offset. Maybe I can do a setter as well function. So something like function array dot let's say if I do count, this is usually a getter, right? So I just have array int. But what if I want to have array and int, right? So just set a new length basically. So it's going to be set. So what do we want to do here is first of all swap. So we have the L and A. Then I want to do something like array.ptr so that we get L and A as a pointer. Ptr.int. Then we have array count.offset plus. We convert it back to a pointer. So we have L and pointer plus 8, I think is gonna be, right? Pointer plus 8. Then we can just swap. And it's kind of the same algorithm. We can just copy it, pointer.storeInt, right? And this thing should just consume everything. So if you think about it, yeah, it's kind of the same thing, right? Like we could return an array here and then we do also this part and this part, but no, I think it's fine. So here I would say maybe array count set, array count set, but wait, we don't need to swap anymore, so it's A and L plus 1. Right, so we just set the stuff, and this shouldn't return anything, and then we can just say true. So I'd say this is the array append function. Hopefully it's gonna work, right? So let's try it. So what did I want to do here? Let's just say that we don't do this stuff maybe, and we just try to use the array. So I do array.init. This should just give me an array. All right, and then I can array append stuff to it. So I can just dupe and then array.append. But array.append needs a PTR. So I could just do one int PTR, and this is gonna give me 1 as a pointer, right? So when it's gonna store it, it's just gonna store it. Okay, that's nice. So it's just gonna store this 1 in the array. Maybe it's worth having like a array show function, but that's not gonna work. I need to do the for loop outside. Yeah, in the future maybe the while loop is gonna be a good good point. So array append is gonna basically just leave me with the A. So I can do array dot count. Right? As I said, I need to implement array count. Array count. It's gonna be just like the stack assembler fd function. All right. So basically array count, I want to convert my array into a pointer. I want to take the count offset, add it to this thing, it's gonna be +8, and then we read from that. So I'm curious, array count show string.std out. Is it gonna work? First try. Well, array capacity. Wait, where do we? Oh, we need the array capacity. That's nice. So that's also array capacity. Right. And interestingly enough, array.items, which should be a pointer, right? And here is the interesting part. I think we don't need to read anything. We just return the address. Fuck. So line 53. I mean, I already said here that what? Left hand side is pointer and boolean. So I have to do, oh, pop2. Yeah, that's true. Array count has non-matching args, expected array but got boolean. So I guess array append also gives me the boolean. So not if any, right? That's the best way to handle show. Isn't it show? Oh, it's int show for some reason. Whatever. So the count is 1, that's nice. And if we append another one, shit, I have to also handle the error. We have a 2. Nice. So I guess we kind of append items in the array at this point. So can we maybe, I guess we have some kind of a array. It's not the best yet. I mean, I have to implement it better, but it's fine. So function should have a name, should have a stack, should have an array, right? And I'm just gonna say the body, right? Or expressions. And if we check main.c, if we go to the program definition, program function st expression is more complicated, which kind of sucks. But let's imagine that we have stack st expression now. This is stack st expression, and the expression is just a string with some kind of, I don't know, number. Let's say we just have numbers in this language. So this has an array of expressions, or at least that's the goal. So let's have a function actually that gets an item. So function array.get has an array index I and gives us a pointer. I would maybe say pointer bool, just to also do error handling in case something happens. So let's swap first. Let's dupe and do array capacity, or dupe and array count. That's important. So we have let's bring it forward, so it's ALI, right? It's ALI. So if it's less than or equal, then it's bad, right? If L is smaller than the index, it's bad. So yeah, pop false, I guess. Zero int ptr. Else v, we should have ptr and okay. So if it's fine, if the thingy is fine, we have to do, we lost the I though. We lost the I, so I'm gonna dupe. So we have I, and in this point we have to rotate. Right, so we have I multiple times now in the beginning, just for the memes. So here I can just pop 2. Right, so now we have I twice. So let's convert A first to a pointer. So we just say array items, right? Array dot items. So we have I and pointer. Then I do pointer to int plus. So now we have pointer plus I. And see, this is the point where maybe size of an item would be nice to have, because I should be, you know, offset. So that's kind of that. So here we are gonna get the item from index I, but it's you know. So here we have the A. So if I do array dot get from 0, let's put a 2. We should get pointer bool. So I'm just gonna do to keep the A going. So let's panic if not. So now we have A and pointer. So if I do pointer int and then int show string.std out, we should see 1 and then size is gonna be 2, but let's store 69, why not? Or like 42 and 27. Let's see. Okay, that's good. What the fuck? Why is it I? 53. That's funny. Oh, int. Obviously. So line 53. So here we have int pointer to int, and then we obviously need to change it back to a pointer. Function array get has non-matching are expected array int but got array. Fuck. Oh, array argument comes first. So we see for 2 and then some crap. Okay, so when we stored, maybe it's bugged. Pointer plus I and append, it's storing. Oh, I mean here we actually store. Wait, what? Here we have a pointer. We convert the pointer. So A is the item. PTR, I said PTR is the item that we want to store. So I converted the PTR to a number and then I stored it. So it means I need to read a point. I need to read from this pointer actually. So we keep it as point, no, int ptr, yeah, that's true. And then if I do ptr.ut int, we dereference that thingy, and then I think we need to somehow convert it back to pointer. So we get ptr plus I back, kind of. So is that? We get 6.9, but then it's also 5.4 for some reason there. Let me just pop 6.9.5.4. That's kind of cool. So something maybe is wrong in the append function. What? Oh, 1 plus. Again, I should probably do something like 8 plus, right? 8 plus 1. Because here 16 means we allocate, oh, it's 16 times 8. Anyways, I think we need to increase the L by 8 anyways, right? So now it's 42. And if I want to get the second item, which again I need to use 8, sadly, it's 27. Right, so that's another thing I would add maybe here, is you specifying the size of. But now we can see some of the things that we can do with this language. I just need to improve the array, and then maybe we can add data structures to it, like the AST nodes, and then we can try to print the AST nodes to assembly. So right now the assembly, it's just the bare minimum, and we need to build up a program and try to run it to assembly. So I think I'm just gonna improve a bit the array, and then next time we can just try to build up this AST together and then print it as assembly. So yeah, why not? Let's see after I manage to do the arrays. So see you next time. Alright, so since the last time I decided to make some changes to the stack language, which I'll show you in a bit. And I've also added a bit more syscalls, so we can make easier applications that use the files, like reading files and writing files. And yeah, let's go through some of the changes that I've made. And I guess the most important one would be related to how we manage the memory. So now instead of having pointers to different data structures, I decided that integers will live only on the stack. Same for booleans because they are just ints. Then only the strings are gonna be pointers, basically. And this way, if I implemented the pointer data structure properly, so I have this alloc function that is just malloc, kind of. It's similar to what malloc does in C. Then we have these functions that are just meant to be used with integers. So for example, if I call store integer or get integer from memory, then I'm able to write into the pointer, so that would be important. I also have memcopy, and this one would be useful for strings. And I think what's cool, you can see that if we implement this pointer properly, like with the base functions, we can implement other more complicated functions like memcopy just by using only these functions. So you can see here that memcopy just copies 1 byte from one pointer to the other. So that's the idea of memcopy. And then we have memcompare, which just compares 2 pointers from one pointer to the other. So that's just how to implement memcompare, right? And the integer stays the same, so it's just an external data type, and it's gonna live on the stack now instead of the heap, right? Same functions, it works kind of the same, nothing really changed. Boolean, it's also the same, hasn't really changed. But for the string type, I thought that, well, maybe it's gonna be a better idea to have it as a data structure. Maybe it's also gonna serve as an example of data structures, and it's gonna have the length and the pointer string. And PTR is kind of, you can think of it as a, well, depending on which function from here you are using, it can be either an int pointer or a byte pointer, or like char pointer, right? So that's the idea. You can cast it from one kind to the other. And another thing that I changed is the compiler will no longer provide you the field getters or the constructor, because I think it's going to be easier to re-implement the language in itself if we don't have to think about how to do that yet. And I mean, I can see some kind of algorithm in here of doing that, but I'm not really sure yet how to handle these if we have pointers or other data structures nested in data structures, because that's going to be the hard part. Like, sure, integers pretty easy, but it's going to be more complicated with pointers. So if we think about FFI, like if we want to get some library of C, we have to be able to build data structures, and the memory management should look like C, basically. So that's the reason. But yeah, I'll try to figure out how to do the field getters automatically, because that was pretty cool. Right. And yeah, the next cool part is that string concat is no longer implemented in assembly, because it just works to use memcopy. I mean, it's extremely convoluted, but it's basically just memcopy, right? So that's kind of nice. It memcopies the first string into the new string, and then it memcopies the second one. So that's the idea. And then substring also is implemented in the language itself, pretty nice. And string this is just a small function I was playing around earlier with. It's basically taking a byte from the string, and you can see that I'm using int type as a byte, which it's not ideal, but I was let's just say too lazy to implement these functions again for bytes. So we can just imagine that if we convert something to byte, we only care about the lower part of the integer, so that's kind of it. And then we can have like string dot equal, right, which is the extremely easy to implement using memcompare. So yeah, and yeah, some util functions to print to standard output, just like helpers. And then we have the syscalls, and as I said, I added open and close. It's not that much, but I think it's going to be much easier to implement syscalls from now on, right? And standard library then, which just has fopen, fclose, fread, fread until end of file, and fwrite. So like these are all the things that we currently have. And obviously I had to fix some of the examples, like rule 110 no longer worked, so I had to fix it, which was, I guess, not that bad. Honestly, I think it's shorter now for some reason, but it wasn't that bad. I had to fix it. And fizzbuzz as well, I had to fix it, but for fizzbuzz it was pretty easy because I just had to fix printing, that's all. So yeah, I guess that's kind of all of the changes, right? I mean, also documented that in the readme, most of the things, right? Kind of don't like it because I have to change it quite a lot, but I think it's nice to have this description of each function, what it does. So I mean, that's kind of the update. And yeah, let's try to start on implementing the language on itself. I think that's gonna be more interesting.